Good morning, friends. Now, the remaining numerical of exercise of this chapter 12, Thermodynamics. Right? Already we discussed about the 12.1, 12.2 and 12.4. Now, the 12.5th numerical of exercise. In changing the state of a gas adiabatically from an equilibrium state A to another equilibrium state B, the amount of the work 22.3 joule is done on the system. Here the work done on the system, therefore this work done is negative. Right? Now, the system is now changing from state A to the state B. Doing this, the net heat absorbed by the system is 9.35 calorie. How much is the net work done by the system in the latter case? We have to find out first the adiabatically the work done on a system that is given 22.3 joule, and then by absorption of the heat, the gas is changing from state A to state B. We have to calculate the net work done. For that purpose, here a gas adiabatically goes from state A to state B. A gas goes adiabatically from state A to state B. So here the adiabatically process takes place, therefore the amount of the heat absorbed is equal to 0. Or the extent of the heat is 0, and work done on a gas. Here the work done on a gas, delta W is equal to minus 22.3 joule. According to the sign convention, if the work done by the gas, that is positive, and work done on the gas is negative. Therefore, from first law of thermodynamics, delta Q is equal to delta U plus delta W. But process is adiabatic, therefore delta Q is equal to 0. Therefore 0 is equal to delta U plus delta W. Here delta W given, therefore change in internal energy of the system is minus delta W is equal to minus, and delta W is minus 22.3, therefore 22.3 joule. That's the change in internal energy of a system. Here internal energy of a system is positive, it means the internal energy of a gas is increases. Here internal energy of a gas increases. Now, second part, the gas changes or goes from state A to state B by absorbing the amount of the heat is 9.35 calorie. Now, a gas goes from state A to state B. State A to state B. The heat absorbed delta Q is equal to, there is given, there is the 9.35 calorie. 9.35 calorie. Convert into the joule. Here the elation is given 1 calorie is equal to 4.19 joule. Therefore, 9.35 into 4.19, that much joule. Now what is the multiplication of this? There is the 9.35 into 4.19. So its multiplication is 39.18 joule. 39.18 joule. Right? Okay. Now delta U is known. We have to find out the net work done in later case. Therefore, the net work done from first law of thermodynamics delta Q is equal to delta U plus delta W. Therefore, delta W is equal to delta Q minus delta U. Delta U already we have, that is the 39.18 joule minus delta U already we found 22.3 joule. So the subtraction is 16.9 joule. 16.9 joule work is done. Net work done by the system. That is the delta W. Now listen, again repeat this numerical. Here the initially, that means in first part, a gas goes from state A to the state B adiabatically. Right? Doing this, the work done on a gas is given, there is the 22.3 joule. So using this concept, a gas goes adiabatically from state A to state B. Here the adiabatic process, therefore the exchange of the heat is 0. Right? And work done on a gas, delta W is minus 22.3 joule. Here negative sign indicates the work done on a gas. From first law of thermodynamics, delta Q is equal to delta U plus delta W. But that is the adiabatic process, therefore delta Q is equal to 0. Therefore 0 is equal to delta U plus delta W. Delta W given, we can calculate the change in internal energy of a gas. Therefore, change in internal energy of a gas is equal to minus delta W. Therefore, minus 22.3, that means the 22.3 joule. That is the change in internal energy of a gas. Here, that is the positive. So we can say that during this adiabatic process, the internal energy of the system is increased. Right? Now, in second part, here the gas absorbs the 9.35 calorie heat and again going from state A to the state B. Here this process is not adiabatic. Now, whatever the net work done in later case, that means in second part. Now a gas goes from state A to state B. A heat absorbed, delta Q is equal to 9.35 calorie. Here we have to convert the calorie into joule. Here the relation is given 1 calorie is equal to 4.19 joule. Therefore 9.35 calorie is equal to how much joule? Therefore 9.35 into 4.19 is equal to 39.18 joule. Now, how do we calculate the net work done? From first law of thermodynamics, delta Q is equal to delta U plus delta W. Therefore, delta W is equal to delta Q minus delta U. Delta Q, already we calculate in joule, the heat absorbed 39.18 joule. And already we calculate the change in or the increase in internal energy is 22.3 joule. So subtraction is 16.9. So there is the work done by the system. In second case, it absorbed the heat 9.35 calorie. Here it is very easy numerical. Okay. Now next 12.8. An electric heater supplies the heat to a system at rate of 100 watt. If system performs the work at rate of 75 joule per second. So at what rate is the internal energy increasing? At what rate its internal energy increasing? Now the heat supplied to the system at rate of the heat supplied to the system in 1 second is 100 joule because the 100 watt is given. In 1 second is equal to 100 joule. Right? Okay. Now, if the system performs the work at rate of 75 joule per second, that means the work done in 1 second is equal to 75 joule. 75 joule. From first law of thermodynamics, delta Q is equal to delta U plus delta W. What we require? We require the what rate is the internal energy increasing. Therefore, delta U is equal to delta Q minus delta W. Right? Delta Q minus delta W. Delta Q is equal to 100 and work done, that is the delta W over case, that is our delta W, and that is the heat supply, that is the delta Q. So 100 minus 75, that means the 25 joule. Therefore, the internal energy increases in 1 second is 25 joule. Therefore, the rate of increasing internal energy is 25 joule per second. Very easy numerical here. Again, we repeat it. An electric heater supplies the heat to a system at rate of 100 watt. What is the power is given? Power, that means the joule per second. Right? Okay. If the system performs the work at rate of 75 joule per second, so at what rate is the internal energy increasing? So here the heat supplied to a system in 1 second is only the 100 joule. That is our delta Q. Now the work done is in 1 second is equal to 75 joule per second. That means the 75 joule. That is our delta W. From first law of thermodynamics, delta Q is equal to delta U plus delta W. Therefore, we can calculate the delta U is equal to delta Q minus delta W. Delta Q is equal to 100, delta W is equal to 75. Therefore, 100 minus 75 is equal to 25 joule. Therefore, the rate of increasing the internal energy is 25 joule per second. Clear? Now the next numerical 12.10. A thermodynamic system is taken from an original state to an intermediate state by a linear process shown in figure. Its volume is then reduced to original value from E to F by an isobaric process. Calculate the work done by the gas from D to E to F. Right? Okay. Therefore, the total work done. Therefore, the total work done by the gas along DE path. Here we calculate the work done for DE path, E to F, and F to D. And then the addition of these three work that gives the total work done. Therefore, the work done along DE path is W1 is equal to D to E. Already we learned in chapter 3 and 4 how we find out the work done in keep from the gap. Right? As the gap of the distance versus time is given, so we can find out the work done is equal to area enclosed by the graph. So here for D to E path, the area enclosed by the graph is this triangle plus rectangle. EF, that is the G, and that is our H. So the work done for D to E is equal to area of DEF triangle plus rectangle EFGH. So it's equal to area of triangle DEF plus area of rectangle EFGH. Now area of a triangle half this EF into altitude DF. EF into DF plus area of triangle height into length into width. Therefore EF into FG. Half EF is equal to GH. So 5 minus 2. Value of F is given. E is 5 and F is 2. 5 minus 2. DF 600 minus 300. 600 minus 300 plus EF, E to F 5 minus 2, and now F to G. F to G is equal to 0 minus 300. 0 minus, 300 minus 0. 300 minus 0. Clear this? Okay. Therefore, there is the half. 5 minus 2, 3. 600 minus 300, 300 plus 5 minus 2, 3 and 300. So it's equal to 450 plus 900. So 1350. That much joule work is done. Right? Second case for D to E we completed. Now E to F path. E to F path. The work done along E to F with the EF path. W2 is equal to area of, for E to F path, whatever the area is enclosed, that is the area of rectangle. Area of rectangle EFGH. But here the volume is decreased, therefore the work done on the system, therefore this work done is negative. This work done is negative, therefore here minus sign. Already we found the area of this rectangle EFGH. There is the 3 into 300, that means the 900 joule. 900 joule. Again, when the system going from E to F, the volume is decreased from 5 to 2. While in earlier case the volume is increased, therefore the both work done are positive. Now in that case, here the volume from going from E to F, or the system goes from state E to F, the volume is decreased, therefore the work done on the system or in the gas. Therefore work done is negative, and already the area of EFGH we calculate, that is the 900. So this 900 joule is negative. And now third, the work done along the path F to D. The work done along F2D path, FD path. W3 is equal to 0. Why? Because the volume is constant. There is the isochoic process. Isochoic process. Therefore, according to this equation, P into delta V, change in volume is 0. Therefore, work done is 0 joule. Therefore, total work done W is equal to W1 plus W2 plus W3. W1 is 1350 minus 900 plus 0 is equal to 450 joule. 450 joule. That is the answer. Very easy numerical. Only we have to keep in mind the concept about how we calculate the work done from the gap of the pressure versus volume. Already in chapter 3 and 4, in the first part we calculate this type of the work done from the graph of the position versus distance. The work done is equal to the area. Work done is equal to area here for the pressure versus volume graph. We have to calculate here the dynamic thermodynamic system is taken from an original state to an intermediate state by the linear process and again to the initial state. Okay. Its volume is then reduced to the original volume from E to F and by an isobaric process calculate the work done by the gas from D to E, E to F, F to D. F to D. Now, first we calculate the work done along the path D to E. That means when the system going from D to E, then the work done E to F, and then work done from F to D. Now, the work done along the DE path is equal to the area enclosed by this graph. Area enclosed is this D, E, H, G, F, D. That is in two parts, triangle DEF and rectangle EFGH. Therefore, W1 is equal to area of triangle DEF plus area of rectangle EFGH. Now, area of triangle half base into altitude. Now, area of rectangle length into width, EF into FG. Now, EF is equal to 5 minus 2 value I given, and DF 600 minus 300 plus EF again 5 minus 2 into FG, that means the 300 minus 0. Therefore, half 5 minus 2 3, 600 minus 300 300 plus 5 minus 2 3, 300 minus 0 300. So that is the 450, 3 3s are 900 by 2, 450 plus 3 3s are 900, so 13,500 joule. That is the work done for D to E path. Now E to F path. Again, the area of rectangle EFGH. Therefore, already we calculate the area of rectangle EFGH, that is the 900. But when the gas going from, or the system going from E to F, its volume is decreases. Therefore, the work done on the gas or the system, therefore, there is the negative. Therefore, we consider this work done W2 is negative for E to F path. Now next, the work done to bring the system from F to initial state D. So here we bring the system at constant volume, therefore the change in volume is 0. That is the isochoic process. Therefore, the work done along the F to D path W3 is equal to 0 because P into delta V. But the delta V is equal to 0, therefore 0 joule. Therefore, the total work done W is equal to addition of these three work done W1, W2 and W3. 1350 joule minus 900 joule plus 0 joule, that means the 450 joule. So friends, here the numerical of this chapter is completed, right? Only the numerical of exercise of this chapter, no numerical in illustrations, right? And what are the important, and also the board suggested this numerical be calculated. Clear?